In this video, we'll be reviewing key concepts relating to computer memory and how it's managed by Rust and the Rust Standard Library. We'll be covering basic but fundamental topics, so if you already have experience with a language like C or C++, then you can probably skip this video. To benefit the most, it would be useful if you've at least covered the first 5 chapters of the Rust book, from getting started through to using structs to structure related data. In particular, you should be familiar with concepts such as functions, variables, and types. For example, integers, structures, arrays, and strings. The first 5 chapters of the Rust book will help you with this. We'll be discussing memory and how it's allocated and accessed in a Rust program, and this will include looking at a couple of small example Rust programs later in the video. Having a basic understanding of how memory works under the hood will help a lot when it comes to learning about things like references, the borrow checker, and smart pointers. When we start looking at the examples later, it'll also be useful to have an understanding of how data in memory can be represented. So let's do a quick review of the structure of a few key data types and their representations. The most fundamental unit of data in computer processing is the bit or binary digit, which can have a value of 0 or 1. Computers have various instructions that can process a single bit. However, the smallest amount of data that can be read from or written to memory is a byte. A byte contains 8 bits, and its simplest interpretation is as a binary number. Binary, also known as base 2, is a counting system that has 2 possible values for each digit. Those are the values 0 and 1 as mentioned earlier. We use the C language prefix 0b to indicate that a number is in binary notation. Each digit's value is increased by a factor of 2 for each position it is shifted to the left, and so a digit's value is calculated by multiplying it by 2 raised to the power of its position. The value of a binary number is then just the sum of the values of the individual digits. Another important counting system that we'll be using later is hexadecimal. Also known as base 16, hexadecimal has 16 possible values for each digit. A digit can specify the value for a group of 4 bits or half a byte, which is also known as a nibble. A hexadecimal digit can have a value of 0 through 9 or A through F, where the letters represent the decimal values 10 through 15. We use the C language prefix 0x to indicate that a number is in hexadecimal notation. Each digit's value is increased by a factor of 16 for each position it is shifted to the left, and so a digit's value is calculated by multiplying it by 16 raised to the power of its position. The value of a hexadecimal number is then just the sum of the values of the individual digits. Shown are some examples of decimal byte values with their binary and hexadecimal equivalents. Rust doesn't have a built-in type called a byte, but it does have 2 types that are the size of a byte. They are the U8 and I8 types. U8 is short for unsigned 8-bit integer. The value of a U8 is the standard binary interpretation of its bits, so in the example shown, the value is calculated to be 82. A U8 can hold values in the range 0 through 255. U8 values can also be found as characters in an English language UTF-8 string. These are commonly referred to as ASCII characters, and they have a Unicode UTF-8 encoding that can fit in a single U8 value. In this example, the U8 value 82 would correspond to the capital letter R. UTF-8 strings can also contain non-English language characters, but in that case, the encoding requires multiple U8 values to store a single character. The I8 is very similar to the U8, except that the most significant bit, bit 7, when set, has its value negated. That is, it has a value of minus 128 instead of 128. In the example shown, the value of the I8 is calculated to be minus 125. The full range of an I8 is minus 128 to plus 127. Rust also has larger unsigned and signed integer types, and the most commonly used of these is the I32. The I32, or signed 32-bit integer, is Rust's default integer type, and is 32 bits or 4 bytes in size. If you don't specify the type of an integer when initializing a variable, then the compiler will, in the absence of any other information, make it an I32. The value of an I32 is calculated in exactly the same way as for an I8, except that there are more bits with larger values. It also has its most significant bit negated, in this case bit 31. To support memory management at the language level, a language must provide one or more types that implement the concept of a memory address, allowing access to specific locations in your computer's memory. The Rust language and standard library have various types that partly or fully comprise a memory address. The size of a memory address is determined by the architecture of the system that your program is targeting. For this discussion, we'll assume that the architecture is x86-64, also known as AMD64. For x86-64, a memory address is 8 bytes or 64 bits in size and can hold 2 to the power of 64 or approximately 18 quintillion distinct values. For technical reasons that we won't go into here, not all of the 64 bits of a memory address are actually used for the memory location. Commonly only 48 bits are used, but that still works out at 256 terabytes, which is the equivalent of the combined physical RAM in 8,000 computers, each with 32 gigabytes of RAM. However, some of this address space is reserved for use by the operating system, and the OS will additionally restrict user address space reservations further for various reasons. Again, this is not a problem for anything we're likely to be doing. In my testing, I was always able to consistently reserve at least 90 terabytes of memory on both a Linux machine and a Windows machine. That's still a huge amount of memory, thousands of times more than the physical memory you are likely to have installed on your system. Reserving a memory range is not the same as using that memory though, and so in practice you will not be able to use more memory than the combined total of your system's physical memory and swap file. A swap file is an area on your permanent storage drive that RAM contents can be swapped in and out of to give the appearance of more physical RAM than is actually available, albeit with a significant performance penalty. On my computer with 32 gigabytes of RAM, I was able to actually use 75 gigabytes of memory, thanks to the swap file. But remember, that's gigabytes, not terabytes, and so represents less than 0.1% of the reservable address space. For certain types of program, it is useful to have an address space that's much larger than the actual memory requirement, or the available physical memory, but that's beyond the scope of this video. It's convenient to represent certain types of values, including memory addresses, in hexadecimal format. Shown is a small section of memory with consecutive addresses and comprising the UTF-8 string Rust with a space at the end, followed by the decimal values 42, 13 and 37. Note the hexadecimal notation for the addresses, but character and decimal representations for the memory contents, but you can choose whatever representation best suits a particular context. In C and C++, if you want to access data using its address, you use a type called a pointer. You can pass pointers as arguments to functions, and you can access the data that they point to by using the dereference operator. The problem with pointers is that they can be used in such a way that they accidentally access data that they're not supposed to, and can even crash your program. Rust also has pointers that behave very similarly to C and C++ pointers, but they're typically referred to as raw pointers in order to emphasize the risks of use. Additionally, if you need to use a raw pointer in a potentially unsafe way, you have to put that code in an unsafe block. This is like telling the compiler, I know what I'm doing and I accept full responsibility. There are certain things that can only be achieved by using raw pointers, but as a 1x Rust noob, you'll want to stay away from them for the foreseeable future. Don't worry though, Rust lets you leverage the power of pointers through the use of smart pointer types provided by the Rust standard library. Although these use pointers under the hood, the public API that they expose is 100% memory safe. The most common way that you'll use memory addressing in Rust is with the reference type. The reference type is part of the Rust language and also provides full memory safety. The most common use of a reference is as a function argument or return value. Instead of copying a large amount of data into and out of a function, only a reference, which contains the memory address of the data, is copied. Okay, let's start by imagining we have a simple Rust program, which you can see on the left. It's been compiled and is waiting to be loaded from disk and then executed. On the right-hand side, we have 3 distinct regions of empty system memory. For the sake of simplicity, in these examples we'll assume that all numeric values, including memory addresses, are 32 bits or 4 bytes in size, and that the size of each of the memory slots shown on the right is also 32 bits or 4 bytes. Remember though that most modern desktop and server systems will typically use 64-bit memory addresses, not 32 bits. Next we see that the program has been loaded into memory and partially executed. The blue colour indicates the current program location on the left and newly updated memory locations on the right. So the doIt function has been called from the main function, but none of the statements in doIt have been executed yet. As a result of this loading and partial execution of the program, the three regions of memory have been initialized and partially populated. This is a simplified version of the actual structure, but it captures the key points of interest to us. The memory region labelled Program contains the program's CPU instructions or code, as well as any data that is part of the program source code. For example, the text string Rust, which is used in the assignment in the last statement of our doIt function. This type of data is described as static, since it can always be found in the same location in memory from the initial execution of your program until its termination. The memory region labelled Stack is where local variable values are stored. A local variable is any variable that is declared within a function body using the let keyword. The variable being local to that function means it cannot be accessed by code outside of the function. The allocation of memory for local variables on the stack and its subsequent deallocation when the function exits is completely taken care of by the compiler. As we go through this example, you'll see that local variables are shown as being added to the stack from higher to lower memory addresses. That is, from the top of the screen towards the bottom. This is because the stack grows downwards in memory. But note that, typically, as an optimization, the compiler will grow the stack for all the local variables in a function using a single instruction, and then order the variables in that memory in ascending order. The last memory region, labelled Heap, is where all other data is stored. That is, data that is neither static nor local. This data must be explicitly added to and removed from the heap as a result of requests by the program. These requests are handled by a software component called a memory allocator. It's the responsibility of the memory allocator to execute and keep track of memory allocations and deallocations, increasing the size of the heap when required. Your program has to store the address of all heap allocations in order to subsequently access the associated data. Stack data and heap data both have their advantages and disadvantages. So let's quickly look at the pros and the cons. There are two main benefits of the stack. Firstly, access to stack data is faster than heap data. This is because the compiler has all the information it needs to keep track of the locations of stack variables at runtime, and so can generate instructions that directly access these. Secondly, allocation and deallocation are automatic and fast. Each requires only a single CPU instruction at runtime, since the CPU has built-in support for the stack in the form of stack registers and stack instructions. There are three main disadvantages of the stack. Firstly, the size of your data must be known at compile time. Secondly, variables are local and so only available in the function they're declared in. And finally, the stack size is limited, so it's possible to overflow the stack and crash your program. There are three main advantages of the heap. Firstly, the size of your data does not need to be known at compile time, since requests are made to the allocator at runtime. This makes it possible to create certain data structures that cannot be created on the stack. The cons list, described in the Smart Pointers section of the Rust book, is an example of this. Secondly, the heap is much more flexible than the stack. You can create your data when needed, then grow it, shrink it, or delete it. And finally, data size is effectively unlimited. You can use all available system memory if you want. There are three main disadvantages of the heap. Firstly, data access is slower on the heap than on the stack. The flexibility of the heap means that the memory address of each allocation cannot be known at compile time, and so your program must store and use these addresses at runtime. This is slow because two separate memory accesses are required to access data. The first access is to retrieve the stored memory address, and the second access is to retrieve or store the actual data. Accessing memory is much slower than executing instructions, so you want your program to minimize memory accesses as much as possible. Secondly, creation and deletion of heap data is slower than with the stack, because both operations require execution of allocator housekeeping functions at runtime. And finally, when using the heap, your program is responsible for allocating and deallocating memory. But note that this is greatly simplified in Rust by the use of smart pointers and standard library types such as vec and string. Now, let's get back to our program, which has executed the first let statement in our doIt function. This has created a local variable I allocated on the stack and initialized to the value 42. I is a 32-bit signed integer with a fixed size known at compile time, and so suitable for stack allocation. Next, we create a local variable A, which is an array. An array in Rust is also of a fixed known size, and so can be stored on the stack. In fact, the data for all local variables is stored on the stack unless there is an explicit request by the program to store part of the data on the heap. The local variable v of type vec is created using the vec macro, where a macro is a bit like a function. Vec, which is short for vector, is a type that is defined and implemented by the Rust standard library. A vec is like an array except that the number of elements can grow and shrink at runtime. V is a local variable, so must be a fixed size at compile time. So how can the number of elements change? The vec's local structure stored on the stack comprises three fixed size fields. A length, which is the number of elements the vec currently holds. A capacity, which is the maximum number of elements it's currently capable of holding. And a pointer, which holds the memory address of the elements that are stored on the heap. The vec data elements have to reside on the heap to allow the number of elements to change. But the reason the main vec structure, containing the length, capacity, and pointer, is on the stack is because the vec was declared with the let keyword, not because the structure is of fixed size. Here's an example of a vec that contains other vecs. The containing vec structure is on the stack as before, but the contained vec structures are on the heap along with their data elements. This allows the number of vecs in the container vec to change. There are a lot of pointers being used here, and we said previously that pointers can be dangerous, but we don't have to worry. Our program does not have access to the internal fields of the vec, including the pointer. The Rust standard library authors do all the tricky stuff for us and then provide us with safe public methods for our program to use. Let's go back to our example program. To avoid frequent reallocations, the vec implementation will typically allocate more memory than is currently needed. In our example, the length is 2 because there are 2 elements in our vec. The capacity is 4 because the vec can store up to 4 elements without having to reallocate on the heap. So up to 2 additional elements could go in the locations shown with a question mark. If we need to add elements beyond the current capacity, then a larger block of memory must be requested from the allocator, with the return pointer replacing the existing pointer in the vec struct. Such reallocations are slow, since existing elements will need to be copied to the newly allocated memory before appending the new elements. The last line of our doIt function creates a variable s, which contains a string slice for the value Rust. We'll talk more about slices and string slices in the next video, but as you can see, the string slice s has a pointer field and a length field. Again, both private, similar to our vec. The length is just the length of the string, which is the 4 bytes of the UTF-8 coded characters, and the pointer holds the memory address of the static value Rust that has been compiled into our program's executable image. I chose a 4-character string so that it would fit nicely into one of the 4-byte memory slots. Before we look at our last example, just a quick reminder that in Rust, variables are not mutable or modifiable by default, so we will be using the keyword mute to indicate mutability. In the example shown, the attempted assignment to j would cause a compiler error. So in this code, we first initialize a variable I with the value 42. As mentioned previously, because we've not specified the type of I, it will default to being a 32-bit signed integer. Next, we initialize a variable j with the value of I. This just copies the value of I into j, so that we now have 2 local variables with the value 42. Note that I and j are completely independent of each other. If we change I, j does not change, and vice versa. Finally, we initialize a variable called iref with a reference to the variable I. The ampersand character is the Rust reference operator. iref now holds the memory address of I. Notice that we used the mute keyword twice. The mute on the left-hand side means that we can update iref to make it reference a different variable. That is, we can change the memory address inside iref. The mute on the right-hand side means that we are creating a mutable reference that can be used to update the referenced value, in this case the value of I. Now we update the value of I using iref along with the Rust dereference operator, which is the asterisk character. Dereferencing iref tells the compiler to operate on the value pointed to by iref. We can only update I using iref because we declared it as mutable and then subsequently took a mutable reference using the reference operator in conjunction with the mute keyword. Doing this, we change the value of I from 42 to 43. Finally, we update iref to make it a reference to j. Note how the memory address is now 4 less than before, because j is 4 bytes below I in memory. If we were now to dereference iref, we would be operating on the value of j rather than the value of I. Thanks for watching, and please like and subscribe so that you don't miss out on the next video, which is on the subject of slices.